Before I do next introduction, may I ask anybody feel cold? Anybody feel hot? You have adapted to Hong Kong environment. Congratulations. Another possibility, the problem already solved by our next speaker, Professor Chandra Sekhar. He was just interviewed by Radio Hong Kong this morning about this phenomenon. Why you people felt cold last night in this room. Actually, it's the same in restaurant in Hong Kong and so forth. So Chandra is a professor in the Department of Buildings at the National University of Singapore. And he is a fellow of ASHRAE and ISIAC. He has been a distinguished ASHRAE lecturer for some years. He worked a lot for ASHRAE. And he is also co-recipient of the Enterprise Challenge Award of Prime Minister's Office, Singapore in 2004. Professor Chandra Sekhar, please.
Thanks, Hugo. I hope you can hear me. I'm using this other mic here. At the outset, I would like to thank Hugo and his organizing team for inviting me to be here to have this keynote talk to this conference audience. It's indeed my great pleasure to do so. This is a subject that I suppose is very close to all of us. We find buildings in hot and humid climates cold, not just in hot and humid climates, in most climates, in summer. And that's sometimes very intriguing. When the outside environment is warm, why should the indoor get cold? Something doesn't seem to be right. So I have an outline here where I basically have a few questions. Really, what is it that we know about people's preference? So looked at some literature and observed some of the findings that researchers have done, looking at buildings not just in chambers, but also in the field. That was my scope at that point. Why do we have overcooled buildings? Well, Hugo just asked if we are at the right environmental conditions. Yeah, suppose we are. I don't feel too stuffy or hot, not too cold, but I'm wearing a jacket. But most of you, the way you are attired, you probably are feeling comfortable depending on where you are seated. Important point. Would raising the set point temperature solve the problem? Let's see what happens there. And I would like to share some strategies, some solutions that we can probably adopt to look at this problem. So if we look at the impact of what we're talking about, thermal comfort in hot and humid climates, we're talking about a fairly large belt on the globe, affecting more than 2.5 billion people if you look at the population in those belts. And not to forget the fact that there are other environments above and below this green shade where the issue could be equally important. And if we combine that with the impact of climate change and what that does to air conditioning demand, we can only look at the fact that energy demand is going to increase, and if we can't do something about air conditioning energy, then we do have a problem in terms of sustainable designs. I put some definitions here which will be useful in looking at some of the literature that I have scouted through. Thermal neutrality, you'll be familiar with what that is. Thermal sensation, a feeling that people express in terms of cold, cool, or warm, hot, a 7-point thermal sensation scale. And then the standard effective temperature, which compares an ideal environment based on certain reference conditions to what happens in terms of the heat loss or heat transfer in the actual environment. So the first question, what do tropically acclimatized people really prefer for thermal comfort? This is an interesting question, I thought, for me, not just looking at it from asking people in a chamber, but also what happens in the field. So in my effort to look at the literature, I asked my PhD student who helped me with this process, look at what's out there as field studies, as environmental chamber studies. The first one that really struck me was this work published in 1953. And interestingly, it was done in Singapore. And I found that here they were looking at what happens in terms of the preference of acclimatized, in this case, British men. And it also involved some Asian subjects at that point in time, apparently, and then later subjects, more Asians working in certain, say, tropical research unit, the medical school. Basically, they seem to have been asked to look at what is their comfort vote, and then the prevailing dry bulb and wet bulb temperature. Simple process of a study that were done for several weeks. And what did they find? They found that majority of the people that they looked at they were pretty comfortable between 22.8 degrees C effective temperature and 25.6. That's okay. That's what we probably would have expected. What is interesting is when the temperature was greater than 28 degrees or so, increasing the air movement from a still to a more turbulent condition added comfort. Remember, air movement, an important aspect of thermal comfort, seems to have been pretty well explored at that point in time, back in the 50s. And then when the temperatures were, say, less than 25 degrees Celsius, still air was more comfortable. So what it really means is we can use air movement over a range of temperature to achieve thermal comfort. It's not just temperature. We know that thermal comfort has several parameters: air temperature, humidity, you have the air relative humidity, the radiant temperature, and there are so many of these parameters besides the clothing that we wear, the activity that we do. So when we look at temperatures in buildings, it gets too cold, we respond to it. It's just one of the parameters that we operate in buildings. So now let's look at some of the other studies that I was able to look at. There were field studies, some from Hong Kong, Malaysia, Japan, and what I really wanted to talk about here was looking at what was the summer thermal neutrality as computed by the research group, and then what was the preferred, in some cases they said the preferred temperature, in some cases it was what was measured. What is obvious here is when you have a warmer temperature, they seem to have used some kind of adaptation to help them achieve the comfort conditions in those places. Some further studies, as you see here in Thailand, there was one case where they observed that the air conditioning room was set at a lower temperature, although the subjects preferred a warmer 26 degrees Celsius. And all of this clearly goes on to say that adaptation is a way by which one was able to achieve comfort in these air-conditioned environments by raising temperatures and using airspeed as a means of achieving comfort. If we then go on to look at the field environmental chamber studies, we heard in the earlier keynote talk by Professor Xu that was another way that most researchers also look at these aspects. There were several studies, so we've done some work, and there's some from States, from India, from Hong Kong as well. And what's interesting is people have looked at what happens when you change certain microenvironmental parameters in the immediate workstation, for instance, relative to what happens in the ambient condition. So there were several studies that talk about, for instance, over here, elevated airspeed preferred for thermal comfort, 23 degrees Celsius. We are looking at 0.3 to 0.4 meters per second. This is one of our own studies there. What we found was when the ambient is warmer, and if we can maintain the correct or most acceptable air temperature around the seated person, there is a much better environmental condition for thermal comfort. And the interesting thing is, if the background is warmer, you find that 26 degrees, it means we can also save energy. So I think the whole notion of achieving thermal comfort in the way we would like to have is to look at both the energy issues as well as what comfort conditions can be achieved. I'll look at some other field environmental chamber studies, and here is some from Brazil, and again, some from Hong Kong locally here. Warmer preference temperatures, preferred temperatures, adaptation with air speeds. So it's certainly becoming one clear process by which adaptation can be achieved with air speeds. This was another interesting observation for me when I looked at it. Those who were exposed to air conditioning at work, their demand for air conditioning actually increases to 88%, from 50%, when the operating temperature is 29.5 degrees. In other words, if you are more exposed to air conditioning, you prefer more air conditioning, generally speaking. And those who are not exposed to air conditioning at work, their demand for, say, natural ventilation decreases only marginally. Well, it could be seen as significant, but relatively speaking, you find that they can adapt to a more naturally ventilated environments if air conditioning is not what they're exposed to work. I put this slide just to have a very quick feel for what's happening in terms of comfort condition that we see in buildings, measurement done in buildings. The red zone is what we find when we have measurements done from buildings. This is where we run buildings most of the time, pretty cold, as you would see here. What we might want to look at is in the same comfort zone, if we can be in the green shade, that's probably a better way for more sustainable design that will get us the thermal conditions we want and also help us be more energy efficient. And the purpose of this slide is just to show where we are in terms of what we do and what is it that you would like to have, like being in the green shade. This is, again, just to reiterate the point about how elevated airspeed can help achieve thermal comfort with warmer conditions. But temperature and airspeed are only two things that we're looking at here. What we are failing to observe here or in these approaches is the fact that humidity plays an extremely important role. And that is where I would like to lead next by basically looking at these three questions. Why are buildings hot and cold in hot and humid climates? Would raising the set point temperature in overcooled buildings be a viable solution? And what strategies we can explore? One of the reasons that we have overcooled environments in buildings is very simply this incompatibility or mismatch between what happens at the air handling unit, in other words, what the air conditioning system has to do, and what we experience in terms of the demand in the space. So here, the role of the cooling coil is extremely critical. The cooling and dehumidifying coil has got to do a very demanding job of removing the heat, both in terms of the sensible heat and the latent heat. And we can look at this as two very simple design criteria. In fact, it's only one criteria, but split into two parts. There is the loads that we see in the space. What do we need to do for the room? What is it that the system has to do? These two must be compatible. They must be matched at all times. The interesting thing about buildings is it's never static, the point made by Professor Zhu earlier. It's dynamic. Things change all the time. Designers estimate a certain design loads, but that doesn't happen in reality, in practice. So when we have these mismatches, we have a little bit of a problem here. What happens with the cooling system, if it is oversized, which is generally the practice, an oversized coil or oversized system is pretty much the norm in most cases, simply because we've got to handle capacity, cooling capacity. So an oversized coil operated to handle a reduced cooling load, or what we call a part load operation in dynamic range, becomes an ineffective coil for handling humidity loads. So it's simply put in this form. The coil is just too big. If only I had the option of going in and changing the coil at that stage, I would be in a much better position to handle the humidity. I'm going to just take you very quickly on the schematic of a sachrometric chart. Don't worry about sachrometrics if you don't follow it. Many practicing engineers and a lot of experts themselves have difficulty in understanding the full sachrometrics of it. But what is it? This is temperature. This is humidity. Going up, humidity increases. Going to the left, we decrease the temperature. So here we have a typical air conditioning process. Outside condition in Singapore, very hot and humid, or any hot and humid climate. We would like to have the space at this condition at 4. This is what you see in front of the cooling coil in the air handling unit. We bring out the air at a certain condition. It comes out into the room at this point, and this is a continuous process that takes place. Now, if everything is fine, that's what we would like to see. This is what the designer estimated. Now, what happens if we have an oversized coil? If we have an oversized coil, we have a situation where the temperature is properly managed and controlled, which is the strategy adopted in most building systems, but the humidity is not. So the space levels go up in terms of its humidity. Instead of 4 being here, you get to see it over there. If you want to address the humidity, we overcool, and that's where the coil comes off, and we cannot or don't use reheat because it's not sustainable practice. Most places you would not be allowed to use reheating for comfort air conditioning. We leave it at that. So that's what causes overcooled buildings. You either have overcooled buildings with maybe the humidity addressed properly, or you have this situation where the humidity is not addressed properly and you have a little bit of a stuffy environment. So this is the hypothesis I'm presenting or starting off with. We have an overcooled building simply because the coil is incompatible. Now, what happens? Can we just raise the set point temperature? I mean, I did show in that schematic that when you raise it, it is theoretically the case that the humidity levels will go up. we did a little bit of a field study to see what happens in terms of people's acceptance. What do they say? So this was a study done in our campus buildings. We were at one time operating on elevated space temperatures, or rather there was a strategy to say, okay, all buildings, we should ideally be operating at warmer temperatures from an energy kind of a mandate. So we were operating our campus buildings at the time about 25 degrees Celsius or so. So I had a student who was keen to look at this whole issue. What happens in terms of thermal comfort, and what do people have to say, and so on and so forth. So there was this protocol. We looked at 7 different offices. We used the ASHRAE 7-point scale for thermal sensation. We had a total of 146 respondents. Some details are presented here. We measured temperatures at 2 different windows of time, morning and afternoon. And we, of course, computed the average PMV PPD values, as well as through the questionnaires obtained the thermal discomfort levels or unacceptability levels. So here are some results. We had a fairly high level of people saying they were not comfortable. And then we tried to see what were the real reasons why that came about. Here you would see here that the temperatures were indeed on the warmer side. So when I said the temperatures were raised in terms of set point, we actually were seeing that in the environments. It was an elevated temperature point. Notice that we didn't have high enough air movement. And that was, to me, very clearly one of the reasons why the discomfort levels were raised in this particular case. We looked at the questionnaire responses, and then the blue column talks about what the people had to say in terms of their own uncomfortable levels or discomfort criteria. And this is the PPD calculation that we were doing with the same measured values. Now, one interesting observation for me here was that what the occupants, they were not subjects, they were actually occupants in the building, what they told through the questionnaire was that it was indeed a lot more dissatisfactory in terms of the levels to them compared to what the PPD said. Now, that's another interesting observation, and there could be a couple of reasons for that observation. That's not what I was focusing on at this point. Just to make the point that the elevated space temperature, only raising the temperature, not doing anything else, did not seem to be a very viable or a good solution to solve the problem. And air movement, as I just showed you through that table, those measurements, was indeed the main reason for thermal discomfort. So here the observations, the humidity levels were also not exactly what we would like to achieve, partly because of the oversized coil part that I discussed with you, and also the fact that the air movement was not quite what would have helped us to achieve thermal comfort. So we know that elevated airspeeds work. There was work done back in the 50s in Singapore that seemed to suggest very clearly that even in air-conditioned environments, we could use air movement. But one important point that I would like to reinforce here is the fact that the humidity needs to be equally carefully understood at this point. This is something I showed you in the literature review as well. This is our own studies where we found that there's a generally higher acceptability level in terms of airspeed for tropically acclimatized subjects. Now, I would like to share, in the remaining part of this talk, some of the, what I'm calling engineering solutions, could be strategies, could be design concepts. These are not by any means a complete list. There could be other strategies, but certain direction that I would like to put forward as part of what I would like to convey this morning. I broke it up into 2 parts, existing buildings and new buildings. It is important that we focus as much on existing buildings as we would for new buildings. A new technology is very easily adapted for a new design. But if you want to talk about something that works well and you want to employ in existing buildings, it's always a challenge. So I look at some of the things that we can possibly do in existing buildings and new buildings quite separately. But there are certain technologies that are common to both, as you see the first 3. I'll go through all of them, taking some time to explain what the strategy is as we go along in the next few slides. So the first one is oversized coil. If we can have a strategy, a technology approach, if you like, that allows us to change the coil or change the heat transfer surface area required in dynamic range, wouldn't that be a great idea? So let's just see what happens here. This was a simulation study that we did a few years back. So here, what you can see is an oversized coil with 200 kilowatts cooling load, because that's what a consultant would typically do. He would never underestimate the cooling requirements, because as a consultant, you're responsible for capacity provision in the building design. So if that's the oversized requirement, or oversized value, the actual load, when the system is installed in the building and the building is commissioned at the operation stage, just before the operation stage, you find that the loads are no more than 100 kilowatts. So that's this red line over here. The blue is what you designed for, red is what you see, and then the actual load with a smaller coil comes down with the green line. So you notice that the smaller coil brings down the humidity level in terms of the state of the air as it leaves the coil. So this is indeed what we are trying to strive to achieve here. So further, it was 100 kilowatts actual installation. It will further reduce because there is a part load operating characteristic of any air conditioning system. Let's remember, it's never a fixed value. It's never as designed. Loads change all the time. So here you're looking at a case where the 100 kilowatts further becomes lower, 50 kilowatts. Blue is what we designed for as 200 kilowatts coil. The same large coil comes off with the red line. So what's the consequence of that? If we use that large coil, the space humidity level goes up. If we were to use a smaller coil, it would come down to this green triangle, and that's where we might get the most effective dehumidifying performance of the same existing coil. We are talking about an oversized coil being able to achieve what we want in practice. How can we do that? We call this the adaptable coil approach, or adaptable coil strategy. A large coil, cooling coil, being able to reduce in terms of its effective surface area in operation. This is a consultant's design for a 200 kilowatts capacity, the large cooling coil. We have airflow from bottom to up on the screen. The chill water flow goes through row 6. It comes out at row 4. We collect it in the manifold. There's a little bit of a manipulation that we do here. The water can go back to row 3 and comes out at 1. If we had the 200 kilowatts load as per design, you have it at installation, at commissioning, no problem. The consultant is happy, everybody is happy if we had the load. But the problem is, the load at installation is not 200, but 100. You need a smaller coil. What can you do? We can do something like this, where we make the large coil become smaller. It's changing the effective surface area of the coil to reduce in terms of what we need. So here we have just these 3 rows being effectively used. These 3 rows exist, but they are kind of static. There's dead water. Nothing is flowing through it. The manipulation of water flow is water goes through to 6, comes out at 4, and then it goes into the modulating valve here. So here is a strategy, very simple strategy that we can employ. It doesn't have to be a 4 to 3, it can be 6 to a 3. It can be a 6 to 4 or 6 to 5 or whatever we think is the right changing characteristics of the coil surface area. Now we combine this with another well-known, well-established theory that we are all aware of. If the airflow through the coil is at a lower velocity, lower Reynolds number, helps the improved heat transfer and mass transfer. If the chill water flow through the tubes of the coil is kept as high as practically possible, this is because too high a velocity pressure drop increases, not a practical solution. So we call it this combination of low phase velocity of the air combined with the high coolant velocity through the coil. Helps in getting the maximum dehumidifying performance of any coil. And these are some of the requirements that I just mentioned. The combination of low air velocity and high water velocity keeps that surface temperature as cold as possible at all times. If the surface is cold, you pull out the moisture a lot more. The condensation is enhanced. You get enhanced dehumidification. So this is basically what the adaptable coil is all about. Let me move on to another technology or strategy that helps us in this process, heat pipes. Some of you may be familiar with it. Heat pipe is a strategy where we just wrap it around a cooling coil. This is called the pre-cooling section. This is the reheating section. There's a refrigerant inside that is in liquid state. It picks up the heat and then it goes over onto, as a vapor onto this side here on the reheater side. It passes its heat to the cooled and dehumidified air, becomes liquid, comes back, and the cycle continues. As long as the coil is in operation, the heat pipe works. It's a passive technology, been found to work reasonably well in hot, humid climates. So it helps us in providing that additional reheat that we would otherwise cannot do. And here it is, the wraparound coil. We'll move on to that. This is, again, a psychrometric way of looking at it. The heat from the outside air is used to reheat the cooled and dehumidified air. We have also developed some other technology which we believe is probably going to be helpful for future designs and developments. When we separate the outside air from the recirculated or cooling air, there's a lot of potential to help us achieve improved performance. So here is something, the single coil twin fan that we have worked on for several years now. It's one air handling unit, one cooling coil, but there are two compartments here. We have the outside air compartment. I'm sorry, I'm using the word fresh air. It's not fresh until it's filtered properly, so the right word should really be outside air, and this is the recirculated air. And as it goes through, we keep them separate until it reaches a zone where we have a way to manage these two air streams based on what's happening in that particular occupied zone. So we have a temperature and CO2 sensor. If CO2 is high, we provide more outside air, and if it's low, we reduce it. What happens in one zone doesn't affect an adjacent or adjoining zone. So it's taking the concept of demand ventilation right up to the individual occupied zones. We have a means of some bypass arrangement here to take care of cooling capacity management if you want to. And here is just a way in which this thing works through the air handling unit. And single coil twin fan, we have had a couple of installations as well, and it seems to be providing good results because the outside air can be pulled down separately. The sensible load, which is really what the recirculated cooling air is handling, allows us to manage them quite separately. And it saves energy simply because we are pulling this out separately and not having to really overcool in that sense. We had some field studies data that I would like to quickly show you here. We were achieving what at that time the occupants chose 23 degrees Celsius here and 50% RH. Very well satisfied. The occupants were pretty well satisfied, and the conditions were achieved exactly what we were looking for. The last strategy I would like to share with you here is about this whole concept of decoupled ventilation system, the personalized ventilation system. We have more talks on this in later sessions of Keynote in this series, but I would like to very quickly talk about it from a thermal comfort perspective here. We have outside air separately supplied to the workstation, and we have the cooling air either coming from the top, conventional design, or it can go to the bottom as an underfloor design. So this is one of our very early studies done in our environmental chamber. The photos just tell what I would like to say in a lot of text. We had subjects come and participate in these studies, and what did they have to say?
3 minutes.
3 minutes. So they found the thermal acceptability pretty good. As you can see with the personalized ventilation, all the blue bars are on the higher side. And they also found the indoor air quality acceptability pretty good. It saves energy because, as I mentioned in the first literature of our own work, when you raise the ambient temperature to 26 degrees Celsius, only work with a personalized environment, it allows us to save energy. Some details here, I will very quickly just mention that in this case, we had a combination of personalized or spot cooling arrangement coming from the top, as well as background from the floor or from the ceiling. Let's see a face level thermal sensation with even with temperatures like 26 and 26, the top over here, as increased airflow, as these are the liters per second of air coming from here, with increased airflow, the acceptability was much better. And the acceptability was better even for the whole body thermal sensation. And this is for indoor air quality acceptability, inhale air quality. So we found that with the spot cooling arrangement, as we use the personalized ventilation, it provided enhanced thermal comfort as well, besides the inhale or enhanced indoor air quality. I found this is the last slide here for the actual content of this particular technology. When we have a cooler ambient and a cooler personalized environment, compared with a warmer ambient and a warmer personalized environment, Let's look at what's happening in terms of preference. People's preference for air movement actually increased. So if you provide them with more airflow, observation that we've been talking about for the last 30 minutes, it works. And even with the personalized ventilation strategy, it worked very well. Of course, when the environments are cooler, people did not really want a higher airflow. So this was very clearly a case where it proved to us that spot cooling, and in this case, achieved through a personalized ventilation strategy, was quite helpful. Conclusions. I'll just like to answer my own questions, which I posed earlier on. Do tropically acclimatized people feel or prefer very cold environments? In my opinion, the simple answer is no. If the outside is warm, why would we want to have very cold environments inside? Why are air-conditioned buildings in hot and humid climates so cold? We discussed about it. An oversized design of air handling unit, an oversized cooling coil, leads to this inability to dehumidify properly. Hence, we overcool to pull the moisture out, leave it at that, people feel cold. Would raising the indoor set point temperature help? Just the temperature alone? I don't think so. We need to take care of the humidity and probably use air movement at these elevated airspeeds. Are there some strategies, engineering solutions? I believe so. It's how we can make use of these technologies implemented in designs, in existing buildings, as well as new buildings, so that we can always be thermally comfortable, do not have to talk about overcooling in buildings, and don't always have to carry a jacket to all conferences. Thank you so much.
Thank you, Chandra. Really like to thank Professor Chandra for the insight. Now I understand how difficult it is to solve